Hello and welcome to Apex Math. Today we are going to talk about how to solve exponential equations with using logs and natural logs. In a previous lesson we talked about how to solve exponential equations by using the same base, and so there's two different ways that you can solve equations when they're exponential. So remember that exponential equations are when the exponent is in the variable is in the exponent position. So in this case, you can see here that this is the variable, what we're trying to isolate here, and he is an exponent. So we can't get to him very well when he's up there high as an exponent, so we have to find a way to deal with that. We have to sort of bring him down out of that exponent position to be able to solve for him. In our previous lesson, we looked at what we can do when we see the bases in the problem being able to be equated to each other. So in this case, we notice that 4 can be rewritten as 2 to the second power. So we could rewrite this problem as 2 to the x is equal to 2 squared, and then that allows us to cancel out the bases because they're the same and just look at the exponents themselves there, and we get x equals 2. Now that is not the type of problem we're going to solve in this lesson, but that is one of the two ways to solve exponential equations. So you need to look at each equation and decide whether or not it can be written with the same base, or whether you're in a situation where that cannot happen. And we are going to look at case 2 when that can't happen. So let's take a look at that. Let's say we have 12 to the x is equal to 13. Now this one, you can see, is different than the last one because there's no way to write 13 as 12 to some power. 13 equals 12 to a power. That can't be done. So we cannot use that first approach. So when that can't be done, the only way to solve this is to work with logs. Logs and exponents go together. So what we're going to do is we're going to take the log of both sides. So if we do log on this side, and I'm going to have to put it over my equal sign here. I'll rewrite my equal there. Log of that side. The reason we're taking the log is because we have a log property that says if I have the log of something to a power, then I can rewrite that as I can take the power and put that in front of the log. So I can rewrite that as 2 times log 5. So it's a way of getting your exponent out of the exponent position and back into the regular line of math where you're doing your computations. And that's exactly what we need to do in this particular case, is we need to get that x sort of that's on the high shelf here off the high shelf and back to where we can deal with it. So by taking the log, we are allowed to then use our log properties and move him from here down to here. But of course, since we took the log of this side, it wouldn't be the same if we don't take the log of this side as well. So now we're going to have x log 12 equals log 13. And remember, when you have a log of a number, don't let that freak you out. This is just a number itself. Log 12 is just a decimal. It's just a number with a decimal. And log 13 is just a number. So this is basically the same thing as saying just x times a number equals a number. Something like this. 2x is equal to 4. That's the same setup that you have right now. This is a number like 2 times x equals a number like 4. It's just log 12 isn't 2, log 13 isn't 4, but it's that same setup. So the way you would solve if you had a number times x equals another number is you would want to isolate that x. So you would make the thing that is multiplied times the x go away. And again, it's whatever relationship here, the log 12 is multiplied times the x. So I want to use the inverse operation to make log 12 go away. So I'm going to go ahead and divide by log 12 because it was multiplied times my x. But what I do to one side of the equation, I must also do to the other side of the equation. So I'm going to divide by log 12 on that side as well. That gives me now that x is equal to log 13 over log 12. And again, that's just a number. So you take that and you punch it into your calculator. Let's clear the screen here. So take log 12 on your calculator, hit the divide key, hit log 13, and punch that into your calculator so it will look exactly like that on your calculator. And you will get the value 1.03 if you round. And that's your final answer. Okay, let's do another one. The next problem we're going to do is 5 times 18 to the 6x equals 26. Now I always like to make sure that I show you that this is no different than if I had 5 times x equals 26. It's just my x right now is tied up here to my 18. So all of this piece right here is kind of stuck together. I like to say it's sticky. This is all stuck together with my variable. But this 5 is not stuck with my variable. The 6x does not relate to this 5 in any way. So I can still get rid of this 5 and make him go away. Just like over here, if I had this to make him go away, I would divide by 5 on both sides. I want to do the same thing here. I want to get the 5 out of the way because he has nothing to do with my variable. So I'm going to divide both sides by 5 and make him go away. So that leaves me with my piece that has the variable in it, 18 to the 6x equals 26 divided by 5. And if I do that on my calculator, I get 5.2. Now the only thing I have left here is tied to my x, because the 18 is raised to this power 6x. So I want to be able to get this 6x that's up there on that high shelf down where I can get to it. So the only way I can get to a variable that's up high is to be able to take the log of both sides. So I'm going to do the log here and the log here. And once I do that, I am allowed to take my 6x, anything that is in that exponent position, and take the whole thing and move it down in front of the word log. So I have 6x times log 18 equals log 5.2. So again, we're looking to solve for this guy right here. So he is now sticky with the 6. If you watch my other videos, you know I talk a lot about being sticky. Being sticky means that he is next to him, and so we want to get rid of the things that are not close to and sticky with that variable. That's the last thing we do, is deal with anything that is sticky with the value, with the variable we're solving for. So we want to get rid of this log 18. So do we divide? Do we minus? Do we times? What do we do? How do we get rid of log 18? Well, we look at the operation here. The operation is times. So that immediately tells us we want to do the inverse operation, the opposite operation to what was already there. Since it was times log 18, we want to do divide by log 18. So I'm going to divide by log 18 on this side, but whatever I do to one, I also have to do to the other. So I'm going to divide by log 18 on that side. So now I have 6x equals log 5.2 over log 18. And if I do that on my calculator, again, simply type in log 5.2 divided by log 18, which I can't write very well there, but that says log 18. If I punch that into my calculator, I get the value. Actually, I don't think I have it written out here, so let me do it real quick on the calculator. I've got log, and then I'm going to push in 5.2 divided by log 18, and press enter, and I get 0.5704. 0.5704 if I round. So now I have 6x equals 0.5704. So let's erase up here to give us some room. And I have 6x equals 0.5704, and we all know how to solve that. That's easy. We just divide by 6, divide by 6. So x comes out to equal 0.095. And that's our solution. All right, let's try another one. All right, the next one I am going to try is negative e to the negative 3.9 x minus 1 equals negative 3. Now, this e here shouldn't frighten you. E is just a number similar to pi, which is a number that we use a lot in math. Pi is used a lot. It's 3.14. And since we use it a lot, we gave it a special name, which is pi. And e is the same thing. It's just a number that we use a lot, so we gave it a special letter name, e. So we're going to look now at what is sticky. So we're trying to get to this guy right here. I'm going to erase that pi because I don't want anyone to get confused why there's a pi on the screen. Alright, so we're trying to get to this. So that guy is in this expression, which is attached to this guy right here. So the thing that's furthest away from this sticky mess here is this minus 1. So that's who we're going to get rid of first. So we're going to do the inverse operation of minus 1, which would be plus 1. So we're going to do that to both sides. So that leaves us with negative e to the negative 3.9x minus 1 equals negative 2. Now, let's go back and again look at what we're looking for here. We're looking for this x. And this is the exponent. And we know we're going to need to bring him down with a log. But remember that unless there's parentheses, an exponent only refers to the thing right in front of it. So this is an exponent on e. It has nothing to do with this negative sign. The negative sign is just like a negative 1 times e. So we can now get rid of that -1 because he is not attached to that exponent, and he's the next closest thing to being near the exponent but not attached to it. So to make the -1 go away, since it's multiplied times the e, we'll use the inverse operation and we'll divide by a -1. What we do to one side we'll also do to the other, so we're going to cross that off. So now we're going to have positive e to the -3.9x minus 1 equals a positive 2. Let's give us some space up here. Now, normally we have been using logs, LOGs, in order to be able to get these exponents that are up here and move them from being up out of the way to down in front. But when we have an e here, that's a special case. We have something called a natural log. A natural log is written as ln. And ln and e are inverses. So they undo each other. So if I take the ln of e to a power, they cross each other off and I just get the power. Or if I have e to the ln of a number, the same thing happens. They cross each other off and I just get the number. So the easiest thing to do here is, instead of using logs, is to use this inverse property of ln and e. So I am going to take the ln of both sides. So I'm going to take the ln of e to the -3.9x minus 1 equals what I do to one side I have to do to the other. So I'm going to take the ln of 2. So the only step I've done now is done the ln of both sides. And again, the reason for the ln instead of the log is because of this e and the relationship between ln and e. Now, instead of just having to bring this down in front like we do with logs, we get the neat trick that these are inverses of each other. They just cross each other off, and this technically is still down in front. So since they crossed each other off, I just end up with -3.9x minus 1 equals ln of 2. And again, remember the ln of 2 is just a number. All right, so now we need to solve for x. So we are going to circle the x here that we're trying to isolate. And we notice that the stickiness is right here. So we're going to leave that till the end. And we're going to get rid of this guy first. So we will go ahead and add 1 to both sides. So now I have -3.9x equals, and the ln, if I do ln of 2 on my calculator, that's equal to 0.693. Again, I rounded. So if I add 1 to that, I get 1.693. And then my last step, of course, to solve in this equation now, to isolate x, would be to just divide by -3.9, divide by -3.9. That goes away, and I end up with x equals -0.4 4, 3, 4. Okay, we're going to do one more, and that will be our last one for this unit. So let's take a look at negative 6e to the 8x plus 8 minus 3 equals negative 23. So this is very similar to our last one. So this, remember, is the exponent for the e, but these guys are all very close to each other, so we're going to deal with that last because they're sticky. So the thing that's furthest away here is this minus 3, and we always take care of that first. So we're going to do our plus 3. So we're going to have negative 6 e to the 8x plus 8 equals negative 20. Now, you know there's a times here. So now I want to get rid of that negative 6. So I can divide through by negative 6. And I am just left with the e to the 8x plus 8 equals negative 20 over negative 6, which if I do on my calculator, I believe is 1.204. All right, so let's erase up here. And remember what the next step is. When you see that e, you are going to use the special type of log. So we are going to take the ln of both sides, because the ln is the inverse, which will allow us to just get to this guy without him being in the exponent position anymore. So I have 8x plus 8 equals, oops, you know what, this was, should have been, sorry, I was one step ahead here. This was 3.3 repeating, and then when I take the ln of it, I get 1.204. So one step ahead with my numbers there. So that negative 20 divided by 6 was 3.333, and then when I take the ln of 3.33 repeating, I get that 1.24 number. All right, so now we are going to subtract 8, and we get 8x is equal to negative 6.796. We're going to divide by 8, and we get our final answer of x equals negative 0.8495. Okay, so just to recap here, when we're solving exponentials, we are going to look for either where we can transform into the same base, and there's a different lesson on that, or we're going to take logs to bring exponent, to bring the variable out of the exponent position. And when we see e, we're going to use the inverse operation of ln. So those are the three things to keep in mind when solving exponentials. All right, all of our videos here are live at Apex Math. I apologize when we do make an occasional mistake, but I hope it was a helpful video, and appreciate it if you would like our videos. If you would like to practice more problems of this type, I recommend Googling Kuta software and looking for their Algebra 2 worksheets. That's where I did my problems from. And they also have the answer key so that you can check your work. If you're a student and your teacher assigns your homework from this, make sure that you are getting the correct answers before you look at the answer key, because the important thing here is that you know what it is you're doing, so when you take your math test that you can get a nice A+. Thank you for visiting us at Apex Math.